Okay, in this part, we'll discuss deep RL algorithms to address the distribution shift problem that we looked at in the last part. So the broad idea towards addressing distribution shift is to be pessimistic, and we'll look at what that means. So in this section, what we'll do is we'll be in the context of actor critic methods, where the Q function is trained with an objective that tries to make it as close as possible to the expected to the target value computed using the reward function plus the expected target Q value under the policy pi phi. And the policy pi phi is updated towards maximizing the Q value, which is shown in the black part of the second line. What these pessimistic methods do at an abstract level is that these methods apply a penalty or a constraint on the policy that is shown in red that prevents the policy pi phi to be very different from the behavior policy pi beta. Such a constraint is known as a policy constraint. So what we'll do now is the policy pi phi is not just trying to optimize the Q function, meaning that it does not try to just optimize the RL objective, but instead it also tries to be close to the behavior distribution, or the behavior policy, pi beta. What does this do really? So let's look back at the Q function profile that we looked at earlier while understanding what the problem is. And let's look at what this kind of a policy constraint would do in this example. So just to recall, the Q function at a particular state is shown here as a function of the action, and the behavior policy pi beta, which is marked as the dashed red line in the plot, which is labeled as beta in the plot. And the issue really was that auto-distribution actions or unseen actions which are erroneously optimistic were being used for the Q function backup. With the policy constraint now, where the policy pi phi is constrained to be in some sense close to pi beta, what is happening now is our target Q function, or our Q S prime A prime, is only being queried on actions A prime, which are in a sense close to the behavior policy or close to beta. So those actions which are farther away and the Q function values are erroneously optimistic, those actions will not be used anymore for the Q function backup. So what we're doing now is we are preventing auto-distribution action values to be used for the backup, and this ensures that all the values that we are using during training are also themselves trained. Because recall from the previous slides that we are training the Q function on state action pairs drawn from the data set, which are drawn from the behavior policy indeed. And now what we're doing is we're also making sure that the target values are computed using these actions. So in a sense, whatever actions we are training on, or whatever actions we are using to compute the regression target for the Q function, are also the actions on which we trained the Q function. So what could be some practical methods, or how can we instantiate this abstract framework of policy constraints into a practical deep RL method that you could actually implement and actually see performing well? So in this policy constraint set of methods, the real choice here is the choice of the divergence D. So pi beta is the behavior policy, which we know. Pi phi is the learned policy that we're learning. But the choice of divergence D, or this notion of metric of, or this notion of closeness, is in a sense up to us. So there are several ways of choosing this divergence D. And these methods can broadly be grouped into these four categories, which we'll go over. The support matching category, distribution matching category, state marginal constraint category, as well as implicit or closed form constraints. So while looking at them, it's beneficial to have this picture here, which is essentially the old picture from before for the Q profile, but it also marks what these different constraints would do schematically on this figure. So let's start with support matching. So support matching is an objective where what you want to do is you want to make sure that the policy that you are learning, that is pi phi, chooses actions that are in the support of the behavior distribution, meaning that the actions that it chooses should be likely enough under the behavior policy. The probability with which the policy chooses those actions, or the probability with which pi phi chooses an action A that is likely under pi beta, may be varying, and that could be either small or large, as shown in one of the yellow curves in the second part of the figure. However, it should choose those actions, it should not choose anything outside. Such a constraint is known as a support constraint, because what it really cares for is it does not care about the density of pi phi of A given S and pi beta of A given S. What it really cares about is just the fact that the action support set should be the same. or or action support set for pi phi should be contained within the action support set for pi beta. An example of such a constraint is the MMD distance, or the maximum mean discrepancy distance, which approximately gives us this behavior. The second form of constraints is distribution matching, which is basically the class of constraints which we typically use, or probabilistic distances that we typically use, like the KL divergence, the total variation divergence, etc. And what these distances would do is they would try to make sure that the distribution pi phi of a given s is close to the distribution pi beta of a given s. And that will give you some behavior like the one shown on the left part of the figure, where one of the purple policies are feasible policies for pi phi, because they are kind of close to pi beta in the density function space. So the density function as a whole should be close towards the density function of pi beta. Unlike the support constraint, where the density function need not be close, except that the support set needs to be contained in the support set of the behavior policy. There are also other alternatives like state marginal constraints, or state action marginal constraints, where instead of just constraining the a given s distribution, meaning that instead of just constraining pi phi of a given s to be close to pi beta of a given s, you can also constrain the marginal state action distribution of pi phi against the marginal state action distribution of pi beta. And finally, there are also methods that implement the distribution matching constraints like the KL, etc., in closed form. So often what happens is that in deep learning, solving constraint optimization problems can be somewhat hard sometimes. So what if you already solved the constraint optimization problem for the policy constraint in closed form and directly implemented that policy update in your code? So these methods do it this way. In a sense, just to sort of summarize, you can always check the paper, the references I marked on the slide, but there are different types of constraints, and they lead to different solutions. And they've provided us with a lot of offline RL methods over the past 1 year or 2 years or so. So one of the next questions I want to go into briefly is which constraint should I use? So we've seen there's so many choices for D, but which of these should we use if I'm a practitioner and I want to apply offline RL to my problem? So before answering this question, let's see what does a policy constraint actually do to the optimal solution, or to the solution that you will recover when you optimize with the policy constraint, when you optimize the RL objective with the policy constraint. So one way of looking at this is this penalized form of the RL objective, where what the policy constraint essentially gets added onto the RL objective as shown in the red mathematical expression here. And you're trying to optimize the policy towards maximizing the expected reward, but also minimizing the divergence T. So it's clear that when you add such an objective, you are altering the optimal performance, because the optimal for this objective may not even be the optimal for the original RL problem without the policy constraint part. And so, therefore, what will happen is the constraint will affect the solution. And what we would want in this setup is a constraint that is least restrictive, while still preventing the erroneous overestimation issues that we saw on the previous part of the lecture. So one of the examples that I would want to go into here is support constraints versus distribution constraints. So if you had a constraint that constrains the supports, as we saw on the previous slide, as compared to a constraint that constrains the distribution. So, and in particular, I would like you to think about this example where your behavior policy takes all actions uniformly. So let's assume we are in a discrete action space, and there are finite actions, and the behavior policy takes each of them uniformly at random. So it's 1 over n, or 1 over a density for choosing each action in your action space. Now, when you constrain the behavior policy, constrain the learned policy to the behavior policy by distribution matching, meaning that you want the density function of the learned policy pi to be close to the density function of pi beta, which is the uniform distribution. What you're really doing is you're saying that the learned policy pi should be stochastic, highly stochastic. It should have density over all the actions, because if it doesn't, then it may then the divergence might be infinite. For instance, the KL divergence would be infinite if you don't have the same supports. So, however, what that would do now is, depending upon the value of alpha that you choose in there, you might end up getting a solution that does not really optimize the RL objective, but is actually kind of super bad, because it really tries to put its most energy towards optimizing the policy constraint. Whereas if you were to use a support matching distance, which said that you can only pick which says that your support set for the actions should be contained in the support set for the behavior policy, but the density could be anything. The density value could just be anything. Then you might end up recovering an optimal deterministic policy for this MDP, because all the actions are seen. So technically, you can just kind of find that one action that is the best, and just find that deterministic policy that only maximizes the RL objective, and also minimizes the constraint by virtue of the fact that the constraint is a support constraint. To formalize this sort of intuition, we also construct an example where something like this happens. For instance, if you have a problem where your behavior policy, where you want to navigate towards the right from a state S to a goal G, and the behavior policy mostly takes the action that takes you towards the left, what might happen now is, if you were to do a distribution constraint solution, your learned policy may have very less likelihood towards going towards the right, because it's constrained towards going towards the left, because of the fact that we are minimizing the RL objective and also penalizing the policy constraint. Whereas if you only did a support constraint, in principle, you can just choose from any of the two actions. And because you have seen what happens when you go towards the right as well, although with very less probability, the resulting policy with a support constraint might still be able to recover the optimal behavior of going towards the right. And the optimal behavior in this problem is to go towards the goal, which is what you really want. So what this tells us is that support constraints might be better in theory, or they are better in theory, because they are not that pessimistic, while also they also give you sort of an adequate balance between optimizing the expected reward and the policy constraint. However, one thing that has been noted is that in practice there's not much of a difference, primarily because you only see one action for a particular state in your data, especially when you have, let's say, image states or continuous states where the exact same image may not be repeated. There'll be some differences for sure. In that case, support constraints may not quite be that effective. And oftentimes what people have found is that it usually depends upon how these general class of policy constraint methods can be tuned. So the performance is very sensitive to hyperparameter tuning, and that is kind of one of the primary issues that makes the distinction between support constraint and distribution constraint methods in practice to somewhat go away. Okay, so now we have sort of covered the broad set of methods that fall in this category of policy constraints, and let's very briefly look at some of the empirical results for these methods. And by no means this is the exhaustive list, and there's a huge, you should actually check out a lot of the papers that I referenced on the slide that actually enumerated different kinds of policy constraints to see what different kinds of methods do in practice. But for this slide, let's look at a simple case where we are operating in the gym environment setting, so on Hopper and Walker environments. And we have a data set collected from a mixture of random and mediocre policies. So what's a mediocre policy? It's a policy that is not the expert, meaning that it does not achieve very good return. But it's also not a random policy, like something that achieves very bad return. So it's kind of like a policy that achieves some intermediate value of return when you on that particular task. And the way we get it is by training an online actor critic agent on these domains, and we stop the training suboptimally at an intermediate point and take that policy checkpoint and use that to generate the data. So in that setting, what we find is, if you okay, and before that, let's look at what methods we compare here. So we compare to a naive off-policy RL method, which is soft actor critic, shown in blue. We compare to behavior cloning, which is shown in yellow, as well as three policy constraint methods, BCQ, BEAR, and BRAC, with the KL version of the algorithm. So that's indicated as KL_VP. And what we see now in these plots is that first of all, doing offline RL using either of BCQ, BEAR, or BRAC is strictly better than behavior cloning. So look at the yellow line versus the other three pink, red, and green lines. It's clearly better, which implies that yes, offline RL can do better than just sort of cloning the data set that you saw. Also note that the dataset average return is shown in the dashed black line in each of these plots, and you're also doing better than that when you run offline RL. Also note that different choices of the divergence D do matter. So the different choices here are the MMD distance, which we saw for the red curve for BEAR, basically. Like BCQ uses some sort of a distribution constraint, And BRAC uses a distribution constraint as well, but it modifies it in a particular way, which we haven't covered in the slides so far. But you are encouraged to check it out in the back paper. And what you find here is that there's sort of like a huge variation, a huge change in performance by using a particular choice of D in the algorithm. Now, these gym tasks are in a sense sort of the main test bed which people have worked on for a lot of years in RL. But let's ask ourselves the question of how do these methods perform on somewhat harder tasks? So what we do now is we look at this task where the goal, and we call this task the ant maze task. And the goal here is to navigate an ant robot or an ant agent, which you have, I'm sure, have had encountered before, with, for instance, in the imitation learning assignment. And you need to train that ant agent to to start from a starting location and go to a goal location. However, the data that you have provided does not have even a single trajectory that can take you from that start location to the goal location. So if you just try to imitate the data, you will not be able to actually get the right trajectory. But you do have trajectories that take you from some location in the maze to some other location. And in principle, you can stitch together these paths to go to the goal. So sort of the stitching motivation that we had earlier. In principle, you would expect offline RL methods to do good here. However, when we actually run these methods on this domain, what we find is that except the simple U maze, which is sort of the U-shaped maze that you see here, on all the other mazes which are kind of larger, really no policy constraint method works that good, and they perform equally badly as equally badly as behavior cloning or naive off policy RL, like soft active fitting. Which makes us question as to why these methods perform poorly in this setup, and how can we improve upon them? Because in a sense, this is the stitching property is what we really want from offline RL methods, and this is the property that is getting us better than the dataset performance, because we can stitch the right parts together to get a better policy than what we saw in the dataset. So hence we ask this question: are policy constraint methods sufficient, or do we need some more innovation beyond them? So there are two limitations that I would discuss here, and the answer clearly is that they are not sufficient. The two limitations are, the first of them is these methods require estimating the behavior policy. So in this constraint, which the policy constraint methods implement, the divergence D consists of pi5, which you probably have because you are modeling that policy as a neural network, or you have the Q function and you can extract the policy pi5 out of it. However, the policy pi beta is not known to you generally, because you are just given a data set. You don't know which policy pi beta generated that data set. And maybe the data set does not even come from a single policy. It can be a data set coming from different policies. For example, a data set coming from different human drivers. And so what you need to do now is you estimate pi beta from the data. So you, let's say, do behavior cloning to estimate pi beta first, and then constrain pi5 against it. This is what typical methods do here. However, if the behavior policy is wrongly estimated, for example, there's some mismatch in what function class generated the data set and what function class you're using, and let's say you're not able to match it or something, then policy constraint methods can fail dramatically, because in a sense, the whole foundation of the constraint is kind of subject to the fact that the behavior policy can be estimated well. And if it is not, then you can fail dramatically. And this is one of the reasons that the ant maze task doesn't work, because the behavior policy is not estimated that great. These methods also tend to be too conservative, which is another reason why these methods are not that great on sort of harder tasks, which means that, so I don't have a great definition for conservative here, but let's consider this simple example that if you let's say your MDP has a certain state where all the actions will lead to zero future rewards. So the cumulative return you'll get by taking any action at a particular state is zero. You don't really care about constraining the policy there, because taking any action will not hit you harder than the other action, because everything is bad. So even while your data took a particular action on that state, you don't care about constraining it. And so putting a constraint on them is just sort of eating up the energy of eating up the capacity of the function approximator to satisfying the constraint, to satisfy the policy constraint, whereas it could have kind of avoided that and tried to optimize the expected return. So in a sense, it is too conservative. So we ask ourselves the question of whether we can do better than policy constraints towards solving the offline RL problem.